All right, it is the last day here of HP Discover. We have our last coffee talk. There will be another discussion a little later, round talk discussion once we're done with this. But we have a coffee talk now on amplifying human capabilities, a whole heap of supercomputing and artificial intelligence. And I don't think we've had a pair of doctors on the stage this week. So we have a pair. Nearer on the right of the picture is Dr. Eng Lim. And on the left of the picture, Dr. Tuomas Sandholm. So I'll just hand it. I'll try not to cough and I'll hand over to you guys.
Thank you all for coming, especially on the Thursday. My name's Eng Lim. I'm the HPE VP and CTO for SGI. Right, HPE acquired SGI, and I have been with SGI now coming up 28 years. But I'm only 6 months old at HPE, yes. I'm responsible for high-performance computing and artificial intelligence at HPE. Yeah.
All right. I am Tuomas Sandholm. I'm a professor in the computer science department at Carnegie Mellon University. I'm also founder and CEO of a startup called Optimized Markets and our startup called Strategic Machine.
So I just, yeah. Mm-hmm. Well, in my area of responsibility, high-performance computing, that we are starting to see a shift. Let's start with what we've been doing in HPC for the last 3 decades. The goal of HPC is to do prediction and forecast, right? Whether this jet engine, when it will fail, or when it needs the next maintenance, whether these gene sequence, right, or the DNA sequence can find a match in its protein expression, right, with a drug candidate. And also weather forecasting. Let's use weather as an example. All these years, in order to predict tomorrow's weather, what we do today is write all the equations that models the weather, measure today's weather and feed that in, apply supercomputing power, and hope to predict tomorrow's weather, whether it rain or not, faster than tomorrow's coming. So that's the goal. Now, in the last few years, things changed because of machine learning. And the idea here is that instead of writing all the equations to model the weather, can you not take the 30 years of history that you have, 10,000 days, and feed each day of your history into the machine learning algorithm and see how the machine guesses whether it will rain tomorrow. It doesn't matter if it guesses it wrong at the beginning, because you have 10,000 tries. And each time it tries and it gets it wrong, it adjusts the weights that dials up and down the individual inputs, right? And eventually, hopefully, you get from a wild guess, and after 10,000 tries, hopefully you get to an educated guess. And once you reach there, can you not then use this machine learning tool that has already learned how to do prediction to predict future? And that has been the shift in the industry. And we see this machine learning towards artificial intelligence approach occurring in many places now, from finance industry all the way to what the professor has been working on recently.
Okay, so we can talk about whatever you want to talk about, but maybe I should initialize it by telling you a little bit about some of the recent work we have been doing on strategic reasoning under imperfect information. So you could think of it as a fairly new category of AI, strategic reasoning under imperfect information, or what I call strategic augmentation. And at least in my lab, it's all geared towards enterprise solutions. And I'm a serial entrepreneur. All of my software companies have been enterprise software companies. It's being a new category. There currently are really no enterprise solutions of this new technology capability yet. Instead, the technology has really made a lot of progress in the last 13 years, and especially in the last 2 years. And this January, for the first time, we reached superhuman level in strategic reasoning under imperfect information in large games. In particular, our AI called Libratus, which is a product of 14 years of research in my lab, beat 4 of the top 10 heads-up no-limit Texas Hold'em players in a game where that's huge and imperfect information. So the game has 10 to the power of 161 different situations that the player can face. So that's 1 followed by 161 zeros. And this has become the leading benchmark in the AI community for testing these application-independent algorithms. So one needs to keep in mind that these are not algorithms for poker. These are algorithms for general-purpose imperfect information games. And by game, I don't mean that it's recreational. It can be very high stakes. I just mean that it is something that can be formally modeled. And applications that we're pursuing now, both in my lab and my new startup called Strategic Machine, Inc., include automated negotiation, strategic pricing. So, for example, currently even companies that are optimizing their multi-item pricing, they're optimizing it as if they're a monopolist or the competitors' prices are fixed, and then they react to competitors' pricing when that assumption fails. Instead, with strategic pricing, you can actually think about this whole pricing planning into the future strategically, where how I should price my items depends on how others price and vice versa. Similarly, product portfolio optimization. If you're a car manufacturer, which product portfolio you should offer and how you should price that really is affected by what your competitors do, which you don't know because they have private information. So that's again an example where the imperfect information game reasoning technology is much more applicable to the real world than complete information games like checkers, chess, or Go. Other applications include certain areas of finance, cybersecurity. We can talk about that in detail if you like. Military applications, of course, auctions, and most recently we have been working on medical treatment planning, where you generate these sequential treatment plans to battle diseases. And we are working on steering a patient's T-cell population to fight cancers, autoimmune diseases, and infections.
The benchmark, right, for the level of where AI has reached, it's games, right? And so far, you've seen what the professor have mentioned. You know, years back, right, IBM's AI system beat the world top chess player, as the professor have mentioned. Few people realized that 2 years before that, the AI software for checkers beat the first of the top world checker player. So you got checkers, then chess. Then people asked, what was the next more complex game than chess? And it turned out to be Go, right? And last year, Google's AlphaGo beat the world one of the world top Go players. And that's a very complex game, right? Now, after Go, then people were asking, is there another more complex game? It turns out that poker, Texas heads up, no limit, right? The one that was selected, is more complex for one important reason. As the professor mentioned, it is an incomplete information game. Why? Because in poker, you don't know the other party's cards. Unlike in chess or checkers or Go, you can see all the pieces. And this is a very important point in business, because if you want to apply the poker AI software to business, it's say in negotiation and auctions, you need the fact that the AI software can handle not knowing what the other party is thinking. And this is quite typical in business. And we are very excited to work together with Professor Sandholm, HPE, to come up with a solution, a platform for automated business application. Imagine in the future, if you are negotiating with someone for a contract online, don't be surprised that at the other end is an AI software negotiating with you. So better develop a smarter one to negotiate for you. Right. Anyway, it's just something to think about, huh?
Yeah, I agree with that. And you get to the point where now that the AI is superhuman in strategic reasoning, you don't really think about the delegation to AI as a time savings or labor savings measure anymore. It's really about better strategic reasoning. And in these high stakes domains, you don't want to delegate some decisions just to save some time. But now that the AI is superhuman, it almost becomes a necessity. It gives you a competitive advantage in your business strategy, in your negotiation, and so forth. And I'd like to thank HPE. We were doing all of our computation on HPE's supercomputers at the Pittsburgh Supercomputing Center. In particular, we were doing all the computation on a computer called Bridges, which is the newest supercomputer at the Pittsburgh Supercomputing Center. And it worked very well for us.
Yes. And actually, there is a story behind that also. I can tell you later.
So hi, I'm Paul Teisch, Tirias Research. Strategic reasoning is an incredibly good topic, but let me ask about the human component. Okay, so these are not provably correct systems, but neither is anybody sitting in the room. Okay, so at least I'm not provably correct. So how will AIs be graded on accuracy, completeness of foresight? I mean, we barely have metrics to measure human capabilities and intelligence. I mean, there's a low bar for passing a driver's test, right? And we've got autonomous vehicles about to hit the road, right? I'm convinced autonomous vehicles are already better than half the drivers on the road. But so could you comment on just how you grade this assistance capability?
For the formal grading, I'll also have Professor Sandholm answer that question, but this is a great question. One of the biggest issue of AI system today is opacity, right? Give you the two examples. When AlphaGo beat the world top Go player, the developer was interviewed after the session and asked, why did AlphaGo make that particular move to beat Lee Sedol? The answer from the developer was, I don't know. Yeah? Right? Because it's opaque. After the training system gone through months of training, right, it comes up with a set of weights to which then you don't quite know what's occurring. You only know that it's been making a lot of good decisions. That's the first point. So it is still an academic problem to be solved. How to make, say, for example, deep learning systems more opaque, more transparent, yeah, from being opaque. That's the first point. So we need to fix that. The work's going on. Papers are starting to be published about fixing it, especially for autonomous vehicles. The second thing about it is, in my opinion, is more philosophical. The question of being a correct answer and a right answer. In my opinion, ultimately, we should be using the AI system as a tool, and the human needs to be there to ultimately make the final decision. Let me give you an example. As you train the system and put it through all the test set questions to show that it's getting more questions right than humans are, you say it is starting to make good, correct decisions. But ultimately, I believe the human needs to be there to decide whether that correct decision is the right decision. Why is there a difference? The difference could be that the correct decision need not be socially acceptable, for example. Right? And this is where we still need to be there for many of the high decision-making, right, systems. The human needs to be there to supervise. Autonomous vehicle will be one example where if it is totally driverless, right, what do we do then? And this is why the making opacity more transparent is going to be a very important point for that. And you can see different companies now working very hard, and they're starting to publish papers just in the last few months, right, to figure out and to solve this problem. Yeah.
Okay, so I'll offer my perspective as well. So that's a great question, and I think about that a lot. And when it comes to our strategic reasoning, your premise is incorrect in that our techniques are actually provably correct. So they have provable guarantees that they will find optimal strategy and they will approach the optimal strategy at this rate as a function of how much computing you allocate and so forth. So these are quite different than, for example, deep learning, where deep learning doesn't currently have any guarantees upfront or after the fact. So in our strategic reasoning, we currently do not use deep learning. Now, I don't want to put deep learning down in that deep learning is especially successful in many applications. And for example, in my other startup, Optimized Markets, when we do advertising campaign pricing, we use deep learning. But deep learning does have the downside as my colleague here mentioned, that it doesn't have provable guarantees. But I also want to drive a difference between provable guarantees and human understandability or opacity, in that those are not the same thing. So when we look at, for example, our poker strategy, the strategy is about a 50 terabyte file. Overall, we have 2.6 petabytes of data stored for various reasons, but the actual one strategy is about 50 terabytes. Now, although we have provable guarantees about the algorithms, it doesn't mean that the human can understand the answer. So those are two different things. Again, provable guarantees of correct working or optimal or near optimal working, and human understandability, totally different things.
And so a question, clarification on provably correct. As with deep learning, it's good at finding local minima or maxima, right? But finding a provable global maxima is more the question.
Great question.
All of these solutions will find some kind of optimal solution, but is it the optimal solution, or can it tell you there are multiple? Right.
That's a great question. So the key point here is superhuman, right? You will realize that the order 170 of poker, the order 161 of poker, right? 161 zeros, and order 170 of chess, of Go, albeit that it is complete information, is not solvable, right? To solve, even if you have the fastest supercomputer in the world today and run it for 100 years, you only solve order 28, let alone order 160. So we know we cannot find the absolute, or we don't know what the absolute global minima is. And we know we're not going to reach that. The key thing is, can we use the AI software to find a minima better than humans? That's the first question. And that's where we are at today. That's why we call it superhuman rather than absolute system, right? So there's a distinction there. And all these games are, you can see from chess, checkers, and Go, it's just to beat humans, right? So like looking for, later the professor can talk about the kidney pairing, right? If you, kidney transplant pairing of donor and recipient, the goal is to make sure that the AI software can find a better match than a human sitting down, even with analytics tools can. Yeah, because the complexity of the problem is so high. And we are not asking for the machine to tell us the absolute best solution, just a better one.
So let me add to that, which is that the algorithms, for example, the equilibrium finding algorithms in the architecture and for strategic reasoning that we have, and the in-game solving algorithms, they actually have provable guarantees. So the equilibrium finding algorithm component says that, okay, as a function of computation time, this is how close you are probably to an optimal answer. And Dr. Eng Lim is right that, to actually get there would take longer than the life of the universe because the game is so big. But along the way, you know how close you are. And it's not a question of local optima. It is bound to the global optimum. And similarly, in the in-game solver, we have this new kind of in-game solving technology with which you can prove that you're not going to be much worse than your original pre-computed strategy, and typically you're much better. Now, there's one piece in the architecture which doesn't give you bounds, which is the abstraction technology up front, where you actually algorithmically abstract the game to make it a smaller game. And we have some papers on abstraction with bounds, but there's still a disparity between the abstraction algorithms that are best in practice and the abstraction algorithms that give bounds. But subject to that small caveat there, all of the algorithms do have bounds, and it's not a question of local optimum. So that's, and in the kidney exchange, we're actually, we can talk about what that is, but in the kidney exchange, our software is making a transplant plan for the country for 153 transplant centers. So 66% of the transplant centers in the country autonomously twice a week. So this is not a recommender engine. It's really saying that this is the plan and this is what's going to be executed. And there we guarantee that it is the provably optimal, globally optimal answer. Not approaching it, but it is the actually optimal answer.
And actually, I'm quite interested in that. Yeah, perhaps it's also for the audience here. Typically, when you have a donor and a recipient, and then you have lots of these pairs, right, in the system, and you want to find an exchange where you get the more compatibility amongst the donor and recipient. So basically, what you need to do is do a reshuffle. Is it what you do?
So in the kidney exchange, it's kind of a long story, but there aren't enough deceased donor kidneys to go around, so you can do live donation. So if you're a nice guy, I can give you one of my kidneys and we'll both be fine. But chances are we're not blood type and tissue type compatible. So that makes us an incompatible pair. And we put all of these incompatible pairs across the country into a database from different transplant centers, and then we try to find at the simplest swapping cycles. So pair A gives to pair B, gives to pair C, gives to pair A. And also we co-invented this idea of never-ending altruist donor chains. So maybe I'm a nice guy and I'm willing to give a kidney without expecting one in return, so I don't even have a patient who needs one. That triggers a chain in the pool. Now, the hard part here is that we can't take more than one kidney out of any donor. So that causes the solution to have to be disjoint cycles and chains. And finding the best combination of disjoint cycles and chains is actually an NP-complete optimization problem where the number of possible solutions is bigger than the number of atoms in the universe. So that is the problem that we're solving with the AI. And we guarantee that we find the 100% optimal solution there.
So we keep using the example of number of atoms in the universe, right? So, that's the reason 10 to the power 170 or 10 to the power 161 is an enormous number, right? I keep emphasizing that because if we, even as I re-emphasize again, if we collected all the supercomputers in the world, bring them all together right now and run them for 100 years, you barely reach 10 to the power 30. That's a number to keep in mind. But chess is already 1771, right? Poker 160. Yeah.
So I'll monopolize it one more time. It's a great kickoff for precision. Okay, precision we expect our Excel spreadsheets. In fact, forecasters today rely overly on extended precision that Excel generates, and we know that all those digits are not significant. But we have that expectation, most people, that computers are precise. So can you talk a little bit about precision in training, precision in running the models, and what level of precision do we get out of these models?
In high-performance computing, when you run simulation, instead of machine learning, you put in your physics equations and you feed your inputs in, you put in supercomputing power in the hope that you can predict the future for that physical system. Right, a lot of times it's just an approximation. Yes, that's a great point. The public thinks the computer is precise. It is. If you have two decimal numbers and you multiply it, in fact, it actually does a rounding right at the far end, right? Because it has only 64-bit precision, right? So actually, the modeling system for high-performance computing using physics equation is an even higher, more level of approximation in there, right? So basically, let's start by saying that there is already a huge amount of approximation. Physics equations themselves are precise at the most basic level, but as you go higher, right, to chemistry, to biology, to thermodynamics, you are starting to approximate more and more now, right? That's the thing. But ultimately, from physics, chemistry, biology, thermodynamics, weather systems, global weather system, solar weather system, and then cosmos, right? And you're starting to approximate more and more because as the system gets bigger and bigger, you can afford less and less precision because you have only the same compute power. Yeah. And I think approximation is something that we have to manage, and therefore imprecision. And that's the reason why more and more scientists are thinking, since we are already imprecise at doing approximations, can a machine do guesses to get you the answer? And don't worry if the guesses are totally out of whack, totally out at the beginning, but I have lots of historical data to keep trying until I get good. And the question is, once you get good on the machine learning side, can it be as good enough to help the simulation on the other side that is physics-based? Yeah. That's the question people are asking. Both are approximations. Can the what starts out to be a very low level of or high imprecision, right? In machine learning, can it ultimately get good enough to help the more precise simulation? Yeah. These are questions that they're asking today. Yes, since we have some time here, I'd just like to bring this particular point about up that we are very honored with the work Professor Sandholm is doing, right? The story goes like that, yeah. 2 years ago, when he started with his first version of the AI software, poker AI software, and competed against the 4 world top poker players, we together lost $700,000, right? That was before. And then the Pittsburgh Supercomputing Center ordered a machine that was 10 times bigger. Then he and his team went back, reworked with the 10 times more compute power, and came back in January of this year against the 4 top poker players and beat the 4 poker players by $1.7 million. So from losing $700K to $1.7 million in that 1 year with 10 times more compute power. This is a very profound thing that really got me to wake up, right? You cannot, humans cannot scale, but you can scale machines. Eh? Well, what do I mean? You cannot, what would be great if a kid in first grade, right, goes to school, right? And then in the morning, and then in the afternoon, he or she comes back with a diploma, a college degree, right? You can't scale humans that way, right? But machine you can scale. In that 1 year, right, from losing $700K to winning 1.7 million, with more compute power. You see, so that really got me thinking, Prof. Yeah.
So now the funding strategy for Carnegie Mellon is to play online poker?
No, we don't have our bots playing online. First, I think it's morally wrong to pretend to be a human when you're not, but also it's against the terms of service of the sites. So we don't cheat with that. I seriously though, so that's one reason. The other reason is that to me, poker is not an application. To me, poker is a benchmark. Much like the chip makers have their benchmarks in the AI community, poker has emerged as, and heads up No Limit Texas Hold'em in particular, has emerged as the leading benchmark for testing these application-independent algorithms for strategic reasoning under imperfect information. To me, the big money is going to be in the enterprise solutions, and all of my startups have been in the enterprise space, as is this one. So that's where I think the real money is.
Yeah, and the use of poker was simply that there's a set of relatively simple rules, and as you've said, the imperfect information requirement that models business processes, human to human processes. So the perfect information stuff is more about the natural systems where you're getting a statistically valid result, whereas the imperfect ones are more about getting something that is better than a human's ability to transact a business process.
I was with you, agreed wholeheartedly, except for the last sentence.
Yeah.
So strategic reasoning, you should not be walking out of here thinking that strategic reasoning is okay once it's just better than humans. In addition to that, it has provable guarantees of being close to optimal or even optimal, depending on the size of the model. So that's. But other than that, yes.
Yes, it's a function of compute power you apply to it, as we were saying, right? If the problem is small and you have enough compute power, you can actually get to a proven global minimum. But if a problem is big and you don't have enough compute power, you get a good enough answer. But you can keep growing your compute power. That's what we're saying, right? You can scale until you get to a global minimum. The question is, are you willing to pay for that power? Yeah.
And you were asking about why is poker such a great benchmark? Well, first of all, I didn't choose it. The AI community as a whole chose it as the leading benchmark. And why? Well, as you said, the rules are fairly simple. in that, a lot of people around the world can understand that, okay, this is the game. We're all testing our stuff on the same game. So now we can see whose stuff works the best. We publish the results, build on each other's research over 14 years now. This really has accelerated the progress by orders of magnitude scalability in the algorithms, not even taking into account the extra boost that you get from the supercomputing advances. So same problem, very large, imperfect information. That's perfect for testing these algorithms.
So with the poker model, you're judging its skill capability versus human players. And when you get to the point where this AI is able to best the best, as it were, a lot of what it's learned has been not just knowing what the simple rules are, but you've got these weird, unpredictable meat machines doing these strange things that it has to learn to best because of these atypical expectations. The next step in my mind is you got to have them playing against each other, the AIs, and see if they can learn from each other, because it's that randomness, the unpredictability, when you bring in that odd human being that just, they're wired differently, that changes the way that the game gets played. It's new tactics, new strategy that nobody would have considered, obviously, because this is net new. Would the AIs actually be able to learn from each other with no other input? Or does it require that truly chaotic meat machine?
So actually, it's the other way around. So the AI started to play each other much earlier. So we started the annual computer poker competition at AAAI, which is an Association for the Advancement of Artificial Intelligence. At their annual conference, we have been playing this annual computer poker competition every year since 2006. So the AIs were playing against each other. And this is at a time where the AIs were way worse than the humans. So there would have been no point us going against the best humans. We would have been laughed out of the room. And for the last 3 years, we have actually won the annual computer poker competition with earlier versions of AIs that were much weaker than Libratus. So but now with Libratus, we can actually beat the best humans. And that's actually another reason why poker is such a great benchmark, in that you have really strong humans to benchmark against. If you go into business negotiation, you could argue that, hey, maybe people aren't that great, or we don't know who the great ones are. Really, everybody thinks they're great. But in poker, you really know that these guys have been playing this game and nothing else. Heads up, no limit, Texas Hold'em, year in, year out. They have millions. That's their profession. They've been playing millions of hands at this, and they are unbelievably good. I didn't even know that with meat as a computing substrate, you can actually be that good.
Yes, and in the deep learning world, right, they have what they call reinforcement learning. In fact, they put two of the machines together and reinforce each other to learn from each other. And that's part of the reason why opacity comes along. So that's related to the earlier question. Let's take an example. In first grade, right, the teacher teaches the student. So the teacher can actually track the progress of the student. But what happens in second grade, the two kids go out and play with each other. The teacher steps back, and 10 years later, the two kids come back. The teacher don't quite know how the two kids have developed. And that's what reinforcement learning gives you. It gives you a stronger solution, right? But then the trainer, the teacher, the humans, right, have stepped back, and you know less and less about the machine after that. So that's the other issue with reinforcement learning. And that's the reason why now there's a lot of work in academic trying to figure out how to fix that in deep learning. Yeah.
Actually, let me pick up on another point just to clarify. You were saying that you need to learn from the opponents. It's not necessarily so. So historically, there were two strands of doing gameplay in imperfect information settings. One was, trying to do opponent modeling and exploitation, which is, I guess, what you're thinking about. And the other was the game theoretic approach. And when the latter really became fully scalable, it beat the pants off the former. So currently, all of the best AIs for poker are based on game theoretic reasoning. And game theoretic reasoning doesn't require any data as input. So if you think about how we created Libratus, it wasn't looking at historical play like in AlphaGo. They were looking at master level plays, things like that. We didn't take any data as input. The only input was the rules of the game, and then you just learn to play game theoretically. And that gives it the generality that it's going to work against any opponent, rational or irrational, and in any application for business, because you don't need to have the data as the input. But now we did have a third module which would actually look at the humans play in aggregate and not trying to take advantage of their weaknesses, because I felt that they don't have very many, but instead to let them show us where our weaknesses are, and then we would supercompute and answer using our algorithms for those parts of the strategy space to have an even closer approximation to game theoretic play. And that's nice in that that's a universal patch. Now that patch, where our hole has been patched, will work against any human, not just those particular humans.
There's not really a tell for a human to use against the machine, is there? The ultimate poker face?
He hasn't even used visual inputs yet to the machine, right?
Yeah, well, we're not using visual inputs, and we also promised the humans that we're not using timing tells, so they can actually think harder at the harder problems, while if you're playing humans, they will pick up on that, the timing. And we said that, okay, you can use any timing tells you think we have. If our AI thinks longer, and you think it signals something to you, have at it.
How do you deal with the white guy problem, the bias that says that there is engineers, there is no women in the algorithm sector, there is not a lot of women, and do you have problems with this bias?
So this is actually an interesting thing. So the AI creates its own strategy. So it's not a male-created strategy or a female-created strategy. It's an algorithmically created strategy from scratch. So we didn't engineer the strategy, and nobody else did either. We just developed the algorithms that automatically created the strategy. And now in terms of democratization more generally with strategic reasoning. So once everybody has the AI, I call it strategic augmentation, that will actually lift worse strategic reasoners, humans, different humans, onto the same playing field. So if you have somebody who's very experienced in negotiation and maybe they have a big chin and are the tough guy, well, now the weaker looking negotiator or really weaker negotiator is going to be lifted to the same level. So in some sense, once everybody has this, it actually democratizes strategic reasoning.
This societal question is brought up quite commonly every time we talk about AI, right? What happens 100 years from now? So there are two parts to this, right? As the prof have mentioned, I think students that come out of school, right? Any student, I think they'll be very good at using tools. If you treat AI as just another higher level tool, you'll democratize things. Essentially, perhaps, right, STEM will still be important to understand the basics of what the AI is in school. And I think humanities studies will become more and more important because we ultimately are tool users. The tool will tell you the correct answer, and we as humans have to then present the right answer to decide using the right answer by applying societal values on that question, on the answer you get from the machine. So that's the first part of it. The second part of it is the question about artificial general intelligence. As the professor always brings up the point about the sword and the hammer, right? These are essentially specific tools. The tools to do negotiation well, tools to do complete information well, tools to drive cars well, right? Very, very specific tools, right? The big question is, if 100 years from now, if you combine 100 different specific intelligence, will you get an emergent property that makes it generally intelligent? Now, this is a more far-reaching question that people do ask, but I think it's further out than we think. But for now, in this generation, next generation, and the next, we'll be tool users, right? And be very good at using these very, very smart tools. And I believe that will democratize society. Right? You look at your cell phone today with all the apps. Right? Think about those apps being individually specific, intelligent apps. Yeah. All right. And then a user now can equal to most of others out there using the same tools.
Yeah, it's nice that Dr. Goh brought up the metaphor. I've been using this saw and a hammer metaphor. So to me, AI is a tool, and it's not a tool for everything. There are different AIs for different problems. And just like there's a saw for cutting wood and a hammer for hammering. And people are worried about AI becoming a super species that is going to take over mankind. But that's more like a Hollywood movie thing. There's no real demand for a saw hammer. A saw hammer would be a worse tool than a separate hammer and a saw. Same in AI. So so I don't think that there's any need. There's no demand for this grand AI that's going to do everything. It's more like a movie thing.
So for these predictive technologies, right now, what's the percentage of accuracy that you guys can get, and where do you think that it's going to go? Of course, you can't get to 100% accurate, but can you get to 99.9%?
So our strategic reasoning is not doing prediction. So that's just reasoning from the rules of the game. So this might be better a question for you.
If you look at checker, chess, Go, and then poker, the transition from Go to poker is there. So that's what we've been describing, right? Before poker and the games before that, there are mostly deep learning, and before that, expert systems, right? So okay, let me start again. Chess is more like an expert system when it won, and then Go more like deep learning when it won. But when it comes to poker, it is more the formal methods that the professor is talking about. And there it is less prediction, but deep learning is. In deep learning, for example, when they send in 10 million pictures of cats and not dogs, but cats, all right, into the deep learning system and keep training and say, you got it right. Is it a cat? No. Adjust your weights, keep going. And then eventually when they got it right, I believe they used up to 10 million pictures, right? They were getting it right about 98%. I need to check the numbers, definitely higher than 90% of the time. So you can get to quite high levels. And looking at that, they were already seeing that they are starting to get as good as humans there. Yeah. So yes. In fact, but people do say that in optical character reading, that was more like AI way back, right? Where you send in a picture of text, and then it converts that into editable text for you in OCR. People do say that even 99% isn't great, right? If you have 1 million characters, that's a lot of errors, right? But in the AI world, in deep learning, they are getting there, right? They are just starting. Why do I say just starting, even though AI has been around decades, right? The reason is because there has been recent huge investments by GPU companies to go into AI because they were looking for an alternative to their graphics market. And then they realized that the deep learning market, specifically deep learning market, applies computing in a very similar way to graphics. Right? And that's how you see recent investment creating a huge wave, right, of interest, re-interest in AI.
Yeah, that's exactly right. So the deep learning market is really driving demand for the GPUs, but it's not. GPUs are not, and deep learning in particular is just a subfield of AI. So if you think about AI as a field, machine learning is a subfield, deep learning is a subfield of that. So, for example, in Libratus, we didn't use deep learning. We used a traditional CPUs in a huge scale in the HPE supercomputer called Bridges at the Pittsburgh Supercomputing Center. But it's not that all AI is based on GPUs. The AI actually drives demand for traditional CPUs as well.
So the hierarchy is as follows, right? Perhaps that was the first thing I should have said, so my apologies. The goal is artificial intelligence. To get there, there are different methods, expert systems and so on, but machine learning, right, is the one that is being highlighted right now. So to become artificially intelligent, there are many ways. One of the ways is machine learning. To learn, there are many ways. one of which is deep learning, and another one is formal methods, as the professor methods are, right? And so this is the hierarchy. So deep learning and formal methods are a subset of machine learning, and machine learning is a subset of artificial intelligence. To become artificially intelligent, the machine has to learn. And there are two methods of learning, many methods of learning, two of which are deep learning and formal methods.
How are we doing? Any more questions for the guys? One of the observations I was going to make is that when you talk about the weather prediction, it's a not quite real-time system, but playing poker is absolutely real-time in response. What things have led to those changes? Is it just that they are different classes of problems, or have there been recent innovations that have made significant differences there? So when we look at weather prediction, it's really, we've got years of trends and we're predicting what's going to happen in the 24 hours time, what's going to happen tomorrow. But when you're playing poker, you can't wait until tomorrow to make your next move. You're being much more responsive. And does that point towards more real-time AI and things like autonomous vehicles, those kinds of applications?
Yes, you're right. You spotted that point really well. So in weather prediction, before the weather station publishes tomorrow's weather, they have to apply supercomputing power to do the calculation, the Weather Bureau, NOAA, and so on. They have to calculate within 3 hours the next prediction, because they have to do 5 predictions a day, right? So they have a 3-hour window to get that calculation right. But so that's not real time, 3 hours, right? Now the goal is to get to real time, all right? Can you do that with machine learning? That's the question, right? Instead of applying supercomputing power to calculate your prediction, can you not use a trained model to infer and do an educated guess at the prediction? And that is a much faster one, right? Because after months of training, right, you can then come and infer very quickly, almost real time. So the inference part of deep learning, it's of high interest to people because they can do it real time. The slow part of deep learning is the learning phase, right? Because they have gobbled up lots of data. But the inference phase after learning is very fast. It's much faster. Yeah.
And similarly, in Libratus, we are also balancing this trade-off by having algorithms both that do computation before and computation during. So before the event, we spent about 15 million core hours of pre-computing strategies for the game. And this is before the match even had started. So we run for months and optimize our strategy. Then as we get into a certain situation in the game, then in real time, we run what we call in-game solvers, which actually refine the strategy and make it even better for the particular end-game that you reach. And then in the background, we actually keep improving the strategies that the first of the 3 modules created. So there's this 3-component architecture where some of the components run offline in advance, some are working online during the event. And nothing is working in real time in the sense of sub-second. But when we talk about real time, it's sub-minute.
And at 11 a.m., Theater 5, the professor will have 3 slides that describe these steps. If you're interested, you can be there. 11 a.m., Theater 5. Yeah.
Well, gentlemen, thank you very much for bringing us some more on artificial intelligence, and particularly it's interesting to see where this is going in terms of applicability to real-world problems rather than just playing poker. So
thanks for having us.
And we'll be back with a little review of what's happened here at HP Discover amongst the bloggers in about half an hour's time.
Thank you.
Thank you all.